Alright, I know we've done a lot already here with just sequences in section 1, but there's still quite a bit more to do. I'm going to try and finish it all in this last video. Next thing I want to talk about are some common limits, and this is a theorem, and there's 6 really common limits that you need to worry about. I'm not going to prove all of these. They are in the book if you're really curious. So the first one is one that we've already did. Natural log of n over n, that goes to 0. Another common one that shows up all the time is the limit of the nth root of n. Let me see how I get an nth root going on here. The nth root of n. So this goes to 1. All right. The next one here, the limit so this x could be anything. It doesn't matter what that x is. But if you have a number raised to the 1 over n power, that goes to 1. The next one here, the limit of x to the n goes to 0. So this one, there's a little bit of a caveat to, as long as your x is less than 1. So if you have a fraction and you keep raising that fraction to the n power, it eventually goes to 1. 2 more here. So the limit of 1 plus x over n to the n power, like that, that goes to e to the x. This one I hope should look a little bit familiar if you've done anything with finances whatsoever. This left-hand side is the, completely blanking on what it's called, compounding interest formula. So this is the compounding interest formula, but if you take the number of times you compound to infinity, you get the continuous interest formula, which is where the e comes into play. All right, one more. So the limit of x to the n over n factorial is equal to 0. And believe it or not, I still have people that have no idea what a factorial is in Calc 2, so let me just explain that a little bit. N factorial is just taking whatever that number is multiplied by the next number down times the next number down times the next number down all the way until 1. There might be some dots in there. So, for instance, if you have 6 factorial, that's just 6 times 5 times 4 times 3 times 2 times 1. So that's a factorial. Factorials are always the biggest things. By biggest, I mean that it increases the fastest. So because this denominator increases so much faster than the numerator does, this whole fraction just goes to 0. Okay, moving on. Recursive definitions. So this is more for like computer programming type of people. So there's 2 parts to this. The first part of the definition is going to be the values of the initial terms. Okay. The second part is a recursion formula for calculating any later terms. So just as an example of a recursive definition, let's say that you're given this: a sub 1 is equal to 1. And a sub n is equal to the previous value plus 1. What this does, this particular example, is that just gives the natural numbers 1, 2, 3, forever and ever and ever. Okay, but there's a million different ways that you can do these recursive formulas. So this should be one that I hope looks familiar to you. I hope at this point you guys are all math nerds and you know everything about math there is to know. Let's say that you have this as the recursive formula. So a sub 1 is 1, a sub 2 is 1, a sub n plus 1 is equal to a sub n plus a sub n minus 1. All right. So think about it, write it all out. I'll just at least write out the first values. So our first value is 1, our second value is 1. The third value is going to be the second plus the first value. So 1 plus 1 has the third value to be 2. And then every single time you're just adding the last 2 numbers together. So then 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so on and so on. And this is a very famous sequence. I hope you've heard of it before. I kind of just gave it away there. This is called the Fibonacci sequence. Did I spell that wrong? How can Fibonacci not be in the word numbers? Oh, because there's only 1 N and 2 C's. I spelled it wrong. That's why. Okay, few more definitions here. Don't want to take the Fibonacci sequence with us. So bounded monotonic sequence. All right, what you need to know about this one is this is just kind of the end all of what the next few lines are about. So don't worry about that for now. Let's define each of these individually. Let's define what it means to be bounded. Something is bounded if a sequence A sub n is bounded from above if there exists a number m such that A sub n is less than or equal to this m for all A sub n. Oh, sorry, just for all n. So a sequence is bounded from above if there exists a maximum m, this is called the upper bound, such that A sub n is always less than or equal to that upper bound. All right, so m, like I said, is called the upper bound. If m is the lowest possible m, then we say that m is the least upper bound. If m is lowest possible m, then m is least upper bound. Yeah, that makes sense. So it's similar for bounded from below. This we just notate with a little m. So little m, we say, is the lower bound. And then if little m is the greatest possible little m, then we say m is the greatest upper bound. Lower bound. Oh, geez, sorry. I don't mean to keep saying upper bound. Little m is the lower bound. This is the value that your sequence cannot go below. All right. Finally, if you have a sequence A sub n is bounded from above and below, then we say the sequence is just bounded. If it is not bounded from above and below, then we say it is unbounded. So even if it's only bounded from above but not bounded from below, we still call it unbounded. It has to be bounded both below and above for it to be considered bounded. Just for a really goofy example of something that finding these least upper bounds and greatest lower bounds are these. So let's look at the fraction or the sequence values. 1/2. The next one 2/3, the next one 3/4, and then so on and so forth. We can define this as the sequence n over n plus 1. Okay, great. Okay, so let's try to find the greatest lower bound. Nope. Yep, greatest lower bound, least upper bound. I always get the wording confused. All right, so pause the video if you want. Think about it for a minute. Let's talk about the greatest lower bound first. These are always going to be increasing. 1/2, 2/3, 3/4. My fractions just keep getting bigger and bigger and bigger and bigger. The smallest fraction that I ever have is this 1/2, and I never go below that 1/2, which means that 1/2 is going to be my greatest lower bound. Remember that your bounds can be equal to the sequence values. So 1/2. The least upper bound. Okay, so these fractions do keep getting bigger and bigger and bigger and bigger. However, they never can get bigger than 1, which means that 1 is going to be my least upper bound. They'll never reach 1, but they will get infinitesimally close to it. Okay, cool. So that's that. If that's confusing, just let me know. More definitions. We're almost done, I promise, with section 1. So, a sequence. A sub n. Oh, I just deleted that whole thing there. So a sequence A sub n is what we call non-decreasing if A sub n is always less than or equal to A sub n plus 1 for all n. Okay, I know that this verbiage here is kind of strange, but it's just what we have. Non-decreasing means that it's either constant or it's increasing. Okay, a sequence is non-increasing if, just flipping that sign around, so A sub n is greater than or equal to A sub n plus 1 for all n. Non-increasing, same kind of deal. So non-increasing, I spelled that really bad, sorry. Non-increasing if my sequence values are either staying constant or they're going down. The sequence is called monotonic if it is either non-decreasing or non-increasing. Okay. Finally, our last theorem, the last thing we're going to write down for this, if a sequence is both bounded and monotonic, then the sequence converges. And I'll kind of draw a little picture to explain what this is. All right. So it's monotonic if it's either going up forever or going down forever. It is bounded if it always has an upper bound and a lower bound that it can't pass through. And if it is both bounded and monotonic, the sequence converges. So just to kind of draw a little, oh God, that's the worst picture ever. Sorry about that. I feel so bad. Just to kind of explain what this is. Again, let's look at the sequence as a graph. Let's say that we do have an upper bound m, that's supposed to be a capital M, that it never crosses. Let's say it also has a lower bound m that it can never cross. So your sequence values always have to be in between these, the upper bound and the lower bound. If your sequence is non-decreasing, non-decreasing means that wherever you start, you can only go up or stay constant. So either we stay constant forever, which means that we do approach a limit and we converge, or we increase. But I can only increase so far because of this upper bound. So I have to converge because I can't increase any further than m. Same thing would hold true the other way around. If I was monotonic the other way and I was non-increasing, which means I'm decreasing down the whole time, wherever I start, I can either stay constant, which means I converge, or I decrease. But if I decrease, eventually I reach the lower bound and I can't go any further, which means I have to converge. So that's what that theorem is saying. If it's monotonic and it's bounded, your sequence will always converge. Okay. Section 1 took 4 videos to get through. The next sections aren't quite as long, but I already warned you that Chapter 10 definitely has the most stuff in it. So really take your time with Chapter 10.